Can you hear me in the back? Okay. Good day. Today we will be looking at the equations for momentum and impulse and the equations for conservation of momentum. This is the equation for momentum and impulse in vector form. Mass times velocity, that is the momentum before the impulse. This integral term, that is called the impulse. And then mass times velocity, that is the momentum after the impulse was applied. This unit, mass over here is a scalar, velocity is a vector, and if you multiply a scalar with a vector, then that product will give us a vector. Force itself is also a vector, and again, scalar times a vector is a vector. So momentum therefore has direction, and impulse has direction, which is why we can write this equation in vector form and express the different components in I and J components, or the different terms in I and J components. Alternatively, we can take this equation and write it in scalar form and then consider the x direction on its own and the y direction on its own. So what are the units over here? If you multiply mass by velocity, we get kilogram meters per second. And that is the momentum. Then this again is the momentum afterwards. And then the term in the middle, that is what we call the impulse. The impulse is denoted by the capital letter I, and it has units of Newton seconds. We can see that because it is the force being integrated over time, so it's Newton times time. Now, kilogram meters per second is actually exactly the same units as Newton seconds. We can see that from Newton's second law. If we sum the forces, and that is equal to mass times acceleration, the units on the left side would be newtons, and on the right side it's kilograms times meters per second squared. And then if we go and multiply this equation by seconds, or if we multiply these units by seconds on both sides, we get Newton seconds is equal to kilogram meters per second. In fact, this equation for momentum and impulse is actually the integral of Newton's second law. So if we take both sides and integrate with respect to time, we get the integral of the sum of the forces integrated with respect to time is equal to the integral of mass times acceleration with respect to time. And then mass is a scalar or a constant. We can take it out in front of the integral, and acceleration integrated with respect to time gives us velocity. And then this term on the left is the impulse. And now, when you integrate, you'd also have an integration constant. So that integration constant would then be the initial momentum plus the impulse is equal to the final momentum. So over here, you can see since momentum and impulse are vectors, therefore whenever you write down these equations, you must also choose a direction in which you write them down, and you must choose which direction you take to be positive. And then to know whether these individual terms are positive or negative, you just draw a free body diagram, and if a force is, for example, to the left, but you chose to the right as positive, then you know that that particular force would produce a negative impulse. Okay, so these are the formulas for momentum and impulse. Let us do an example based on these formulas. For problem 1513, for a short period of time, the frictional driving force acting on the wheels of the 2.5-ton van is 600 t squared newtons. If the van has a speed of 20 kilometers per hour when time is 0, determine the speed 5 seconds later. So for this problem, we are given force, we are given velocity, and we then have to find the new velocity after a certain amount of time. So we need to find an equation which combines all these parameters. The force is known, the time is known, and now we need to know what is the velocity. So the equation that you would pick that combines all these parameters would actually be the equation for momentum and impulse. As you can see, here we've got velocity, we've got force, and we've got time. So since motion occurs in the x direction, we will set this equation up in the x direction, and for that we need a free body diagram first. There would be weight acting down, the normal force acting up, and then the driving force being developed by the tires. That would be in the direction of motion. And those are the only forces on the free body diagram. Now we would like to use this force, which acts in the x direction, to find the final velocity in the x direction. So we use the equation for momentum and impulse in the x direction. mvx1 plus the impulse in the x direction is equal to the momentum, or the final momentum, in the x direction, from the initial time 0 to the final time t. Then we fill in all the parameters. It is 2,500 kilograms, and the initial speed is 20 kilometers per hour. Now remember that the units over here should be meters per second, so we should convert the speed from kilometers per hour to meters per second, and then that gives us 20 over 3.6 plus the integral of this force, which is 600 t squared, from 0 to 5 is equal to the mass 2,500 times the final velocity in the x direction, and that gives us Vx2 to be 15.6 meters per second. Any questions? Problem 1510. The 200 kilogram crate rests on the ground, for which the coefficients of static and kinetic friction are 0.5 and 0.4 respectively. The winch delivers a horizontal tying force to its cable at A, which varies according to this graph. Determine the speed of the crate 4 seconds later, and originally the tension in the cable is 0. They give you a hint. First determine the force needed to begin moving the crate. This function, or this tension, which is a function of time, would start at 0. So initially the tension developed in this cable would not be sufficient to cause any motion, because the static friction here will first need to be overcome before the crate starts moving. So to tackle this question, we first need to find the point in time where the crate actually starts moving, and that is when the friction force will be at its maximum limit. So the friction diagram looks like this. And on the y-axis you've got the friction force, on the x-axis you've got the applied force, which is acting in this cable. And when this crate is on the verge of slipping, then it would be operating at that point, for which the friction force is equal to mu s times n. So we need to first figure out the normal force, which we get by summing the forces in the y direction. The forces on this free body diagram would be the weight, 200 kilograms times 9.81, the normal force acting down, then the tension in this cable would be twice the tension in each of these cables, because the tension throughout that cable over here would be the same, T. So you'd have T pulling to the right over here and T pulling to the right over here. So this crate will experience a force of 2T to the right, and that would be opposed by the friction which acts to the left. So first we need the normal force, and for that purpose we sum the forces in the y direction. Then we get n minus 200 g is equal to 0, or the normal force is equal to 200 g. Next, we go and sum the forces in the x direction, and we consider the point over here just before it actually starts to slip. So when it is still in the static region, and when it is not moving yet, the sum of the forces would still add up to 0. This would be when it is on the verge of slipping, but not quite slipping yet. Then the forces in the x direction would be 2t minus the friction force, which is minus mu s n, is equal to 0, and we get 2 times the expression for the tension, 400 t to the power of a half, is equal to 0.5 times the normal force of 200 g. And solving for t out of this, the time where the crate starts moving would be 1.5037 seconds. And now we should consider the range of motion from this point in time all the way to 4 seconds only. For the first 1.5 seconds, the crate won't move, so only from that point to 4 seconds is where we apply the equation for impulse and momentum. We take to the right as positive, and then it becomes mvx1 plus the sum of the integral of the forces in the x direction is equal to the final momentum in the x direction. And now here we have to integrate from the point in time where the crate starts moving to the final time. And initially the crate was at rest, so that the momentum in the beginning is 0. And it is this velocity that we want to find. So we have 0 is the initial momentum, and the forces would be the 2t acting to the right, minus the friction, which is now the kinetic friction once it is in motion, so minus mu k n dt, and we integrate this from 1.5037 seconds to 4 seconds is equal to the mass times the final velocity of the crate. And then this becomes the integral from 1.5037 to 4, 2 times the tension, which is 400 t to the power of a half, minus the kinetic coefficient of friction times the normal force, 200 g, is equal to 200 Vx2, and in this equation Vx2 is the only unknown, which you can find as 6.62 meters per second. Any questions? That brings us to the concept of conservation of momentum. Conservation of momentum we use when we are dealing with either collisions or explosions. So when parts initially were moving together and then split into two parts which move independently, or when they initially moved independently and then become entangled together. And for conservation of momentum, you would like to take this equation and find a way to eliminate this intermediate term. And we are able to eliminate this intermediate term by considering the system as a whole. So if you've got two parts, part A and part B, and they are either colliding or exploding, then they would be exerting forces on one another. So they would also, so for example, A would exert an impulse on B, and B would exert an impulse on A. Now these two forces would produce impulses in opposite directions, but equal magnitude. So you can call the one I prime and the other one I, and I prime would just be negative I. if we now go and consider the system as a whole, so if you consider pod A and B together, and we choose the system boundaries around both of them, then these two impulses become internal forces, which allows us to cancel them, and that then means that this term in the middle falls away. And when that term falls away, we just have that the total momentum in the beginning is equal to the total momentum at the end. And important here is that you take the total momentum in the beginning, so the mass times the velocity of pod A and the mass times the velocity of pod B in the beginning, and do the same in the end. And then this equation over here, that is the one known as conservation of momentum. And it only works if you do consider the parts together, that this intermediate term falls away. If you were to consider, for example, part A only, then this impulse would actually cause the momentum of A to change. Or if you were to consider part B only, then this impulse here would cause the momentum of part B to change. So the momentum of the individual items is not conserved, but the momentum of the entire system is conserved if you consider it as a whole. So let us do question 1540. Here we have two canoes which are initially at rest, and two people which are initially not moving with respect to the canoes. And now the boy over here jumps from canoe A over to canoe C and lands on canoe C. So as he pushes himself off, he will get a velocity to the right, while he actually pushes canoe A to the left. And then as he lands in canoe C will move to the right. And we must now find the final speeds of both canoes once he has landed in canoe C. So as he jumps off the canoe A, that's basically a collision taking place where two parts which were initially together become disengaged. And then for that, if we consider the boy and the canoe together, we can use conservation of momentum. They say the boy jumps off the canoe at A with the velocity of 5 meters per second relative to the canoe as shown. That doesn't mean he moves 5 meters per second, say, as seen by the girl or as seen by this canoe. It just means with respect to that canoe A, he moves 5 meters per second at that angle. But since canoe A is actually moving to the left, he would be moving, say, a bit slower than the 5 meters per second, because as he tries to jump off, the canoe would give away under his feet, so he won't actually be able to retain that exact velocity. Let us go and consider the explosion as he jumps off the canoe at A. As he jumps off the canoe at A, we consider the canoe and the boy together. The boy will exert an impulse in this direction on the canoe, and at the same time the canoe will exert an impulse on that direction on the boy. But if we then consider the boy and the canoe together, then those two become internal, and we don't need to worry about these internal impulses. So if we consider the canoe and the boy together, then we can say that the total momentum for these two is being conserved. And we then just work in the x direction only. The sigma signs means we must consider both the momentum of the canoe C and the boy B, but initially both of them are at rest. That is now before he jumps, and before he jumps both of them have a velocity of 0, and then once he is in the air, the canoe would have a velocity and the boy would have a velocity which is different to that of the canoe. So this is then the mass of the canoe times the velocity of the canoe in the x direction plus the mass of the boy times the velocity of the boy in the x direction. And we then get this to be the mass of the canoe is 40 kilograms, VC x, and the mass of the boy is 30 kilograms, and we can then use relative velocity to find an expression for his absolute velocity. We know that VB is equal to VC plus VB relative to C. These are all vectors, so we can then take just the x component of that equation and write it as VBx is equal to VCx plus VB relative to C x. Sorry, actually this canoe is labeled A. Okay, and now we can take this equation and sub it into the expression for the boy's velocity. It becomes the canoe's velocity plus the relative component of his velocity. Now they say the magnitude over here is 5 meters per second, and he jumps off at an angle of 30 degrees. And finding the x component, we use cos of 30. And then this equation allows us to find the velocity of the canoe. So solving, we get VA to be negative 1.856 meters per second. And this negative sign actually makes sense because we chose to the right as being positive, but this canoe would obviously move to the left when the boy jumps off the canoe to the right. Okay, now we need to also know what is the velocity of the boy in the x direction, so we use this relative equation and figure out what the boy's velocity would be. It would become VBx is equal to VAx plus the x component of the relative velocity, which is then negative 1.856 plus 5 cos 30, and that means the boy jumps off with an absolute velocity of 2.474 in the x direction. Okay. Now since the boy does not have any acceleration in the x direction, therefore that would also be the velocity at which he lands on the next canoe. That next canoe is labeled canoe C. So his x component is the same as before, and now we consider the collision between the boy and canoe C. Initially, the boy is moving while canoe C is at rest, and then once he lands on the canoe, then the boy and the girl and the canoe move together at a combined velocity. But on the left side, we have to consider the three parts separately. So the boy has a mass of mb and a velocity of xb in the x direction, and then the girl and the canoe together are at rest. That is before he lands, and then once he lands on that canoe, then they all move together. So we just combine the mass of the boy and the mass of the canoe plus the mass of the girl times their combined velocity, v combined 3. And you just fill in to find out what is the final velocity at which the canoe would move. That is the 30 kilogram at which the boy is moving, times the velocity 2.474 plus 0 is equal to 30 plus the mass of the canoe plus the mass of the girl times their combined velocity. And that gives us the combined velocity after he lands to be 0.781 meters per second. And since we chose to the right as positive, therefore this means that this velocity is actually acting to the right. Any questions? One more, or do you have enough? Okay, one more. Question 1539 deals with another collision. Here we've got a bullet being fired into a pendulum, which is initially at rest, and then it is observed that this pendulum swings up to a maximum height, or to a maximum angle of 6 degrees, and based on this observation, we should estimate the speed of the bullet before it was hitting the block. Now, here we've got a collision taking place, and then once the collision takes place, this pendulum moves up to that highest position. We should actually define 3 separate positions for the things taking place over here. So the position 1 would be directly before the impact. Then the position 2 would be directly after the bullet became embedded in the pendulum, but the pendulum is still directly below its hinges, so the angle would then still be 0. And then position 3 is when the pendulum, together with the bullet, swing to their highest position. And that would be when the angle is 6 degrees. So as the bullet, or as the motion occurs from position 1 to 2 and to 3, then we have that from position 1 to position 2, that is when a collision takes place. And when a collision takes place between these two objects, we can use conservation of momentum and say that the momentum of the bullet and the block together will be conserved. Energy would not be conserved while that collision takes place, and momentum would be conserved. Then from position 2 to position 3, as this pendulum swings up, we can say that energy is being conserved because the only forces acting on that would be weight and the normal forces in these tensions. The normal forces in the cables won't be doing any work, and weight is a conservative force. So from position 2 to position 3, we can say that energy is being conserved. We need to therefore apply 2 principles. From 2 to 3, we say energy is being conserved. And from position 1 to position 2, we say momentum is being conserved. So let us first start off with the conservation of energy as an object, or as a system moves from position 1 to position 2. And then we say that the total mechanical energy in this position is equal to the total mechanical energy in that position, since no energy was removed or added. It was just converted from kinetic to potential energy. So T2 would be the kinetic energy of the block and the bullet together when they start moving from down here, and that would then become a half times the total mass times V2 squared, and then V2 is the potential energy of the system, which is mgh. To express h, we need to choose a datum, and we can choose a datum, for example, at the initial position, say through the center of gravity over here. And then h, the height, is measured positive up and negative down. And if the object initially is at the datum, it would have no gravitational potential energy. And then the kinetic energy at the highest point would be 0, because that is when it reaches the maximum angle, and then it will swing back. So it will temporarily come to rest and swing back down. So the final kinetic energy is 0. And then V3 is the potential energy at that highest location, which you can write as mg times the height that it reaches. Now, if this is 1.25 meters in length and that angle is 6 degrees, you can write this as 1.25 times 1 minus cos of 6 degrees. That's basically this distance here. That's how far it moved up. This would again be the total mass, which is the 4 kilograms plus the 2 grams combined. And using this equation, we can find the only unknown V2 to be 0.3665 meters per second. That would be the velocity of the pendulum and the bullet combined directly after the bullet became embedded in the pendulum. Now we need to work back from position 2 to position 1 to find out what is the initial speed of the bullet. And for that we make use of conservation of momentum. That is the momentum of the combined system directly after impact and directly before impact. So directly before impact, it was only the bullet moving while the pendulum was at rest. So we use this in the x direction, and we say it is the mass of the bullet times the velocity of the bullet plus the mass of the pendulum times its velocity, which was initially 0 before the bullet became embedded in it. And then after the impact, they move together, so it's the mass of the bullet and the mass of the pendulum combined times their new velocity, V2. And we found V2 to be 0.3665 meters per second, and that allows us then to find the velocity of the bullet to be 733 meters per second. Any questions? Thank you.